Andy, take that L.
I was luck.
Oh,
Rematch.
Okay. As you saw earlier on in our episode, me with my amazing pool skills had beaten Andy at a game of pool. However, have you ever really thought about the science behind pool and how force, work, and potential energy can all play into them? Well, that's what you'll find out today on this episode. Rodriguez, the scientist. Rodriguez, the scientist. In the previous clip that we are going to show you is my winning shot. And from there, we got all the data that we needed. By already knowing the ball's mass, which is 2 grams, and by, acceleration on Earth, we already know its normal force. However, how do we find velocity? Well, right before we were going to hit the ball, we had a timer going on for the second that we hit the ball with a pencil and the second that I hit the wall. With that, we were able to know the time that it took for the ball to hit the wall. And we pre-recorded our distance. By having this change of distance over time, that gives us velocity, which was 2.6. So with that, we basically set up everything that we needed to know, whether it was work, whether it was normal force, whether it was potential and kinetic energy. We already figured that out. So, Andy, with my winning shot, the mass of the ball was 2 grams, and at the velocity that I hit the ball was 0.6 meters per second. Well, the normal force of that ball with gravity and its mass is 19.6 newtons. That's how we beat you.
With your winning shot, the momentum was 0.12, in which the ball was 2 grams, and the velocity the ball traveled was 0.6 meters per second, which is weak.
So Andy, knowing our mass and velocity, we can find our kinetic energy.
And how so, Melissa?
Well, this question is simple. We already know the equation of kinetic energy. 1/2 times mass times velocity squared. We have our mass and our velocity, so the equation is just plug and chug. So after you multiply out all the variables, our kinetic energy, the second that the ball hit the wall was 0.36. And knowing that energy is conserved, we could say that our potential energy the second that the pencil hit the ball is also 0.36 joules. Okay, so we already know our force of the ball and our potential and kinetic energy.
Right.
But what about work, Andy?
Well, work is simply easy. Work is just force times distance. We already know our normal force, which is 19.6 newtons, and distance where the ball was originally from and where it hit, where the displacement of the ball where it hit the wall, which is 0.48 meters. So calculating force times distance, 19.6 times 0.48 is 9.408 newtons.
Down above. Well, Andy, with knowing all this raw information that we calculated, we could also find out the acceleration with a quick plug and check. So we know our initial velocity was 0 since the ball was sitting on the floor. Our final velocity we found through our distance and time, which was 0.6. We also know that our time is 0.8. So there we could also find out acceleration just for fun.
Right.
So the equation is just simply just plug and check. So final velocity 6.8, initial velocity 0, acceleration is unknown, and our time is 0.8. So once you combine all like terms, on the right side of the equation will be 0.8 and our variable 8. On the other side it's 0.6. So all we have to do to find our acceleration is divide each side by 0.8, which will give us 0.75 meters squared, which was the acceleration of my shooting ball.
Good job!
Because I know that grading sucks, Rodriguez, I'm gonna add in some spicy bloopers just to make up your day. You're welcome in advance. For real, Susana?
Oh my god!
Okay, so
Oh.
You got